Imagine finding a footprint in fresh concrete, deep, unmistakable, except the person who made it hasn't been born yet. No one alive could have left that mark. No one who has ever lived. And yet, there it is. That's what LIGO found on November 12th, 2025. A gravitational wave signal, the ripple left when two black holes spiral together and collide, with one detail that changes everything. At least one of the objects in that collision weighed less than our Sun. That should be impossible. Black holes form when massive stars collapse at the end of their lives. The lightest black hole any known stellar process can create is roughly 2.5 solar masses. Below that, you get a neutron star. Below about 1.1 solar masses, you get nothing at all. There is a gap in the compact object mass spectrum, at a no man's land where nothing in known physics can place a black hole. Astrophysicists have been staring at this gap for decades. It was supposed to stay empty. LIGO's signal landed squarely inside it. You clicked because LIGO may have detected something that shouldn't be able to exist. By the end of this video, you'll understand exactly why, and why that 1-2-second ripple in space-time might have just told us what dark matter actually is. The answer has been hiding in the first 10 microseconds of the universe's life. LIGO doesn't see black holes, it feels them. Its twin detectors, one in Livingston, Louisiana, the other in Hanford, Washington, measure ripples in space-time by detecting changes in distance smaller than 1/10,000th the width of a proton. When two massive objects spiral together somewhere in the cosmos, and the universe itself flexes, LIGO catches that flex. Signal S251112C AGM triggered alerts at 3 observatories across 2 continents on November 12th. The waveform analysis extracted what physicists call the chirp mass, the combined gravitational signature encoded in the wave's shape. That number, between 0.1 and 0.87 solar masses. The probability that at least one object in the merger had a mass below 1 solar mass. Greater than 99%. In nearly a decade of gravitational wave astronomy across hundreds of confirmed detections, nothing like this had ever appeared. What happened next tells you something about how seriously the community took the signal. Dozens of telescope teams pointed instruments at the sky region where it originated. The Einstein probe scanned in X-rays. Lead Black Gem and the Wide Field Survey Telescope covered optical wavelengths. The newly operational Vera Rubin Observatory swept over 700 square degrees of sky. They found supernovae, background events, but no kilonova, no afterglow, no trace of a neutron star collision. Whatever merged that November night left no light behind, just a ripple in space-time and a number that shouldn't exist. So what leaves a footprint where no foot should exist? 2 astrophysicists at the University of Miami think they've found the answer, and the way they approached it is the key. Magaraggia Cappelluti, an associate professor of physics, and Alberto Magaraggia, his PhD candidate, published their analysis in the Astrophysical Journal in 2026. And they didn't just look at S251112CM and say, this might be primordial. They asked a sharper question. If primordial black holes are real, if they exist at the abundance the theory requires, exactly how many detections should LIGO have made across its entire observational history? Their answer came back, roughly 1, and the observed count is exactly 1. Park that number. We'll need it in a few minutes. First, we need to understand what a primordial black hole actually is, and why the universe would produce one at a mass scale that no star can touch. Picture the universe at 10 microseconds old. 100,000th of a second after the Big Bang. Every galaxy, every star, every atom of matter that will ever exist is compressed into a space not much larger than our solar system. The temperature is 10 trillion degrees. The matter isn't atoms or molecules. It's a screaming hot plasma of quarks and gluons, the most fundamental building blocks of matter, all flying free, unbound, crashing into each other billions of times a second. And then, the universe cools through a threshold. Around 150 million electron volts, the quarks suddenly lock together into protons and neutrons. Physicists call this the QCD phase transition, the quantum chromodynamics era. In an extraordinarily brief window, the fundamental texture of matter changes. Here's why that moment created black holes. During a phase transition, the pressure of the cosmos briefly drops. Pressure is what fights gravity. When pressure weakens, gravity wins. And in a universe that dense, gravity doesn't need much of an edge. And any pocket of space that happened to be slightly denser than its surroundings, not by much, just a fraction, could collapse in on itself. Not because a star died, because the universe itself was heavy enough to crush space into a point. Think of it like a crowd in a stadium where everyone suddenly sits down. If you're one of the few people still standing, the force holding the crowd apart just vanished. You collapse inward. That's what the QCD transition did to overdense patches of the early universe. These are primordial black holes. And here is the detail that makes them a perfect suspect for S2 51112 cm. The mass of a primordial black hole depends on how much matter was enclosed within the cosmic horizon at the moment it formed. At the QCD transition, at that specific temperature, at that specific moment, that mass is approximately 1 solar mass. Read that again. The QCD epoch specifically and naturally produces black holes at exactly the mass scale that no stellar process can create. There is a gap in the compact object mass spectrum. Too light for stellar black holes, too heavy for neutron stars, and primordial black holes born during the QCD transition fill it like a key in a lock. That is not a coincidence the researchers are hand-waving. It is the center of their argument. The question we parked earlier, what could possibly produce something this light, has an answer. Not a dying star. The universe itself, in its first 10 microseconds, before a single proton had cooled into a stable atom. The idea has a long theoretical history. As Soviet physicists Yakov Zeldovich and Igor Novikov first proposed primordial black holes in the 1960s, Stephen Hawking expanded the framework in the early 1970s, connecting very small ones to what we now call Hawking radiation, the quantum mechanical process by which black holes slowly evaporate over cosmological timescales. For 60 years, the theory sat waiting for evidence. No one had ever caught one. Until, if Cappelluti and Magaraggia are right, a Tuesday afternoon in November 2025. But how do you build a case on a single signal? Remember the number we parked at the end of the last section. Here's where it pays off. The obvious objection is immediate. One signal in 4 years is barely anything. One data point doesn't prove a population. How do you build a serious scientific case on a single event? Cappelluti and Magaraggia's answer is precise. They modeled a population of primordial black holes with a mass distribution shaped by the QCD epoch, accounting for subtleties of early universe lepton flavor asymmetries. Then, they calculated 3 quantities. Every single one matched the observed data. Box 1. The detection rate. If primordial black holes exist at the abundance the theory requires, the abundance needed to make them a meaningful fraction of dark matter, Subsolar mergers should be extraordinarily rare. These objects, while potentially numbering in the trillions across the observable universe, are spread through an enormous volume. The odds of two finding each other, spiraling together and merging within LIGO's detection range are tiny. Magaraggia ran the numbers. The predicted detection rate across LIGO's sensitivity during its third observing run, approximately 0.8 events per year. The observed rate across the full LVK dataset, all 4 observing runs, nearly a decade of data, works out to 0.23 events per year, with a 95% confidence interval that extends up to 1.1. The predicted value sits inside the observed range. The boxes overlap. Checkbox 2, the mass range. QCD-era primordial black holes cluster around the solar mass scale, subsolar, in exactly the range where S251112 centimeters, chirp mass of 0.1 to 0.87 solar masses sits. Not 10 solar masses, not 100, less than 1. The prediction and the measurement point at the same number. Checkmark box 3, electromagnetic silence. Primordial black hole mergers produce gravitational waves and nothing else. No light, no X-rays, no radio emission. Our Einstein probe found nothing. Black Gem found nothing. Vera Rubin found nothing. Dozens of independent telescope teams searched S251112, CM's sky region, and came back empty. The silence is complete. Checkmark rate matches, mass matches, silence matches. 3 independent predictions, 3 independent confirmations. If any one of them had failed, the case would weaken substantially. All 3 held. And there is independent corroboration. A separate research group published their own analysis of S251112 CM in March 2026, also concluding the signal is consistent with a primordial black hole merger in the 0.1 to 1 solar mass range. 2 groups, 2 independent analyses, compatible conclusions. If this is the kind of breakdown you want to see more of, where we check the data instead of just repeating the headlines, subscribe to Cosmic Tide. And we do this every time. Now, Cosmic Tide viewers know to ask, what could go wrong? The signal's false alarm rate is roughly once every 4 years. That's significant, but it falls well short of the 5 sigma gold standard that defines a discovery in physics. The final parameter analysis from the LVK collaboration on S251112 CM has not been publicly released as of late March 2026. Some astrophysicists believe this could be instrumental noise. Alternatives exist, a white dwarf consumed by a black hole, for instance. But these require their own unusual physics and don't fit the data as cleanly as the primordial interpretation. Cappelluti is measured about it. We'll need to detect another such signal, or even several others, to get the smoking gun confirmation that they are real. But what is clear is that they cannot be excluded as being real. That is the scientific status today. 1 signal, 3 matching predictions. And if you follow the logic to its conclusion, this doesn't just explain S251112 CM. It opens the door to the biggest unsolved question in all of physics. For 30 years, the working assumption has been that dark matter is a particle, something exotic, weakly interacting, invisible to every instrument we've built, but detectable if we wait long enough and build sensitive enough detectors. The search has consumed billions of dollars. Underground laboratories, Antarctic ice telescopes, the Large Hadron Collider. Some of the most sophisticated physics infrastructure in human history has been waiting, in silence, for a single dark matter particle to nudge a single atom. Not one has. What if they've been looking for the wrong thing entirely? What if dark matter isn't a particle at all, but trillions of ancient black holes, scattered invisibly through every galaxy, each one lighter than the sun, each one older than every star in the sky? That is exactly what Cappelluti and Magaraggia are pointing toward. Their research indicates primordial black holes could account for a significant portion, if not all, of dark matter. Not a footnote, a direct quantitative claim. And their model places a hard floor on it. If S251112cm is confirmed as a real astrophysical event, that single detection already places a lower bound on PBH abundance. They would constitute at least 4% of all dark matter. That is the minimum. The actual fraction could be substantially higher. What does that do to every dark matter experiment ever run? But they haven't failed. They've been looking in the right place, the cosmos, with the wrong instrument. LIGO wasn't designed to solve the dark matter problem. It was built to listen to stellar collisions. But if those collisions involve objects no star could create, the implications spill far beyond gravitational wave physics. The instrument built for one purpose may have accidentally provided the first answer to a completely different mystery. Picture what that would mean. Right now, this moment, trillions of invisible black holes, each lighter than the sun, each older than every star in the sky, drifting silently through the Milky Way, through every galaxy, holding them together not by shining, not by colliding, but simply by existing, by warping spacetime just enough to keep the stars in their orbits and the cosmic web intact. And this idea has deep roots. Zeldovich and Novikov proposed primordial black holes in the 1960s. Hawking refined the theory in the 1970s. A March 2026 paper in Physical Review D, an independent analysis of the full LVK dataset, found that PBH dark matter fractions are constrained by existing data, but not excluded. The door has always been theoretically open. S251112cm is the first time anyone has produced positive observational evidence to walk through it. If the primordial black hole interpretation holds up, if future detections build a statistical population consistent with QCD-era formation, that is not a small adjustment to cosmology. It is a candidate answer to one of the biggest questions in all of physics. The substance that holds galaxies together, that outweighs every star and planet combined, that scaffolds the large-scale structure of the universe. It might not be in a particle detector. It might be everywhere already. And we may have been passing through it our entire lives without knowing it. One signal is suggestive. 2 would be a pattern. 3 would be a revolution. LIGO continues observing, with sensitivity upgrades that will widen its reach for faint subsolar mergers. But the instruments that could definitively settle this question are still being built. In 2035, ESA and NASA plan to launch LISA, the Laser Interferometer Space Antenna. 3 spacecraft, flying in a triangular formation, separated from each other by 2.5 million kilometers. LISA's arm length isn't 4 kilometers. It spans a significant fraction of the distance between Earth and Venus. It will be sensitive to gravitational wave frequencies that no ground-based detector can touch, opening an entirely new window, including, if they exist in sufficient numbers, the steady background hum of primordial black hole mergers stretching across billions of years of cosmic history. On the ground, Cosmic Explorer, a next-generation American observatory with arms 10 times longer than LIGO's, is in design. When operational, it will detect mergers all the way back to the epoch of the first stars. That is the exact window where primordial black holes, if they shaped early cosmic structure, would have left their deepest marks. Cappelluti says his team hopes this work will aid in confirming that primordial black holes actually do exist. What confirmation looks like is specific. Multiple subsolar detections, forming a population whose mass distribution, merger rate, and spatial clustering match QCD-era formation models. If they find that population, it won't just confirm primordial black holes. It will tell us, after 60 years of theory and decades of failed particle searches, what dark matter is. Here's what we know today. On November 12th, 2025, spacetime carried a 2-second message to 3 detectors on 2 continents. The message described a collision involving an object lighter than the Sun, an object no dying star could have made, a footprint in the concrete of the cosmos, left by something that predates every star, every galaxy, every planet that has ever existed. 2 researchers in Miami saw that footprint and recognized it as real. The first one just knocked on our door.